Hi, I'm Sam Gunn, and I'm going to be talking about commitments to quantum states. So this is joint work with Nathan Drew, Fermi, and Mark Zhandry. Okay, so first of all, what is a commitment to a classical message? Well, a commitment to a classical message is a sort of cryptographic analog to a locked box. So it should enable the following functionality. A sender should be able to put their message into a commitment, or like a locked box, send it to the receiver, and then at some later point they should be able to send some opening information, which the receiver can then verify, and if it passes verification, open the commitment to recover the message M. Okay, so typical commitment schemes come with two security properties, hiding and binding. So hiding says that the commitment reveals nothing about the message, meaning before you receive the opening, the receiver doesn't know anything about the message. And binding says that the sender can't change the message after sending the commitment. Okay, so commitments are perhaps the most fundamental building block for cryptographic protocols. In this talk, we're going to ask, is it possible to commit to quantum information? Okay, so what we want intuitively is basically the same thing, exactly analogous to the classical message case, except now we're going to be committing to quantum states. So throughout this talk, I'm going to write pure states with kets, but really everything applies more generally to entangled states or mixed states, whatever. Okay, so following a standard way of building quantum primitives from their classical counterparts, we could try quantum one-time padding our state psi, and then classically committing to the keys. So this is a folklore scheme, and let's see it in a little more detail. So say that the sender wants to commit to a single qubit state psi. Now she's going to sample bits A and B and a random string R, and then she'll quantum one-time pad the single qubit state with her with the bits A and B, and then send that state along with the commitment to the bits A and B. Okay, now later to open, she can send A, B, and R. Now the receiver can just classically verify that A, B, and R are a valid opening for the commitment they received earlier, and then if so, they can go and recover psi using A and B. So is this secure? Well, remember that hiding says that the commitment reveals nothing about the state, and indeed the classical commitment to the bits hides the bits A and B. So from the receiver's point of view, after receiving just the commitment, the state should still look totally mixed, totally random, because it's still hidden under the one-time pad. Okay, and what about binding? Well, binding says that the sender can't change psi after sending the commitment. And indeed, because the sender has to send the state, it seems like the only thing they could do in order to open to a different message would be to change the bits A and B. But this is exactly what the classical commitment says that they can't do. So okay, so intuitively it would seem like this is a binding commitment scheme. But there's still a big problem with this, which is that it's totally unclear what binding even means in this situation. The textbook binding definition totally fails for quantum states, and we would have no idea how to use this statement that the sender can't change psi to compile cryptographic protocols. Okay, so our current understanding of commitments to quantum states is we have one folklore construction and no idea what security means. So in this work, we're going to try to remedy this by providing a theory for quantum state commitments, or QSCs. So first, we'll argue that binding means that committing to a state psi erases psi from the sender's point of view. And using this definition, we'll be able to first of all show that the folklore commitment scheme we just described is indeed a hiding and binding QSC, and we'll also be able to construct the first succinct QSCs. And by succinct, we mean that the commitment is shorter than the message we're committing to. So as a bonus, we'll actually be able to do this all with one-way functions or potentially even weaker. So this is in contrast to the classical setting where succinct commitments require collision-resistant hash functions. And it's believed that one-way functions are weaker. Okay, and we're going to be able to show, importantly, that our commitments are exactly what you need to compile commit-and-prove protocols with quantum proofs. And as an example, we'll show that succinct QSCs and probabilistically checkable quantum proofs imply succinct quantum arguments. So a succinct argument is just one where a prover is able to convince a verifier of some statement super efficiently, and a quantum specific argument is one where now the proof is allowed to be quantum. Okay, and the benefits of using our quantum succinct arguments are threefold. First of all, they'll use only 3 messages rather than the classical 4. Second, we'll use weaker assumptions, so that's just inherited from the fact that a succinct QSCs use weaker assumptions. And finally, we'll be able to handle classical or quantum proofs, of course. Okay, and all of this is at the expense of using quantum communication now. Okay, so how should we define binding for quantum states? Let's first recall the classical definition. The classical definition says that it's hard to produce a commitment and 2 valid openings to distinct messages M0 and M1. So a naive idea would be to just make everything quantum, put kets around everything. And now what we would have is, we would say, it's hard to produce a commitment in 2 valid openings to distinct states psi0 and psi1. But okay, there's a lot of problems with this definition. First of all, the message is quantum. So now that the message is quantum, it's not clear how to check that psi0 and psi1 are actually distinct. Second, the commitment is quantum. So if you verify the first opening, that could destroy the commitment, and then you wouldn't have any way of verifying the second opening. Okay, and third, maybe most importantly, now that the adversary is quantum, we have to consider a broader class of attacks. So for instance, what if an adversary is able to open to one, or to commit to one message, and then either open to that message or decide to apply some operation and open to a different message? Now, it could be the case that this operation that they can apply destroys the first message, or the first opening. So now they would have no way of simultaneously producing openings to both psi0 and psi1, but they would still clearly break binding because they're able to decide on the fly which state they want to open to. Okay, so at this point, it's not clear that a definition should even be possible. Maybe we'll have to throw our hands up and just resort to reasoning case by case whether a particular commitment scheme will compile our particular protocol. Okay, so fortunately, that's not going to be the case. And we're about to get to our definition, which we call swap binding. Before we state our definition, let's just establish the syntax for QSCs. So if we want to commit to a message psi, there will be some unitary comm, which we apply to psi along with some auxiliary 0 state, and then we interpret the output registers as C and D, the commitment and decommitment. So we'll commit by sending the C register, and then we'll decommit by we'll open by sending the decommitment register D. Now the receiver can verify the commitment by undoing the comm unitary, checking that the auxiliary state is all zeros, and recovering the committed message psi. So it turns out that any QSC can be written in this form by purifying the interaction. With this syntax, our definition, swap binding, says that the D register alone hides the underlying message state psi. That is, if you're just given the D register, you can't actually learn anything about the underlying message. So formally, this is specified with a security game, where an adversary starts by sending the challenger both C and D. The challenger is going to check that C and D form a valid commitment, which just means undo comm, check that the auxiliary state is all 0. And then the challenger is going to randomly decide whether or not to swap the adversary's underlying message with junk or not. So by that would just mean they open up, they undo the commitment, they either swap or don't, and then they close everything back up by applying the comm unitary again. And then they're going to return just the D register to the adversary. So we say that the scheme is swap binding if, for any efficient adversary, they can only guess whether their message was swapped or not, with basically the trivial advantage of 1/2. Okay, but remember that we said binding was supposed to intuitively mean that the sender cannot change their mind about the message after sending the commitment. But we're telling you that binding is specified by a game where the adversary tries to guess whether the message is the one that they chose or some random junk, given only the D register. But so why is binding formalized in terms of something about like learning about psi when it's supposed to say something about changing psi? The reason for this really goes back to a fundamental principle in quantum mechanics, and that is that the ability to learn about a state and the ability to perturb a state are in some sense equivalent. So if imagine that we have some state which is in some way restricted from you, so maybe we're computationally bounded, or maybe we only are given part of the state or some limited physical access to the state, um, then if we have the ability to perform some measurement where the result of the measurement depends on the state, then we have the ability to implement some operation which will change the underlying state, and vice versa. So in our setting, this says that if we can perform a measurement on the D register alone that depends on the state, then we can perform an operation on the D register alone that changes the underlying committed state, and vice versa. So taking the negation of this, we see that the inability to learn about information about the state, given just the D register, is equivalent to the inability to perturb the state, given just the D register. But look, on the right side, the inability to perturb the state is sort of capturing our intuitive notion of what binding should mean, that you can't change the committed state. On the left side, the inability to learn about the state is what we formalize with swap binding. But the crucial thing that happened here was that whereas we talked about the difficulties of formalizing, of making a security game in which we test an adversary's ability to perturb the state, we saw that it seemed very difficult, but on the left side, we already showed you a very clean, simple security game which captures the adversary's ability to learn about the state, and that's the swap binding security game we saw a couple slides ago. So we've converted this sort of nebulous thing that we didn't have a grasp on to something very concrete that we can test. Okay, and swap binding turns out to have many additional nice properties. So first of all, remember we said binding means that D hides the state, and I didn't define hiding for you, but hiding should say essentially the same thing about the C register, that the C register hides this underlying state. So the fact that these two properties are just equivalent is what we call the hiding and binding duality, and this has a lot of nice consequences. So another very important property about our commitment schemes is that they handle entangled messages very nicely. So as an example, imagine that a sender has some EPR pair, and imagine that they commit to each half of their EPR pair separately. So it turns out that even though each commitment only sees a single qubit maximum mixed state, we're actually bound to the entanglement between them. That is, if we open both of these separate commitments separately, then we will be guaranteed that the openings are to the two halves of the same single EPR pair. Okay, and it has a bunch more nice properties that are all very useful for us. Okay, we already saw a folklore construction of hiding and binding QSCs, but what about succinct QSCs? Classically, succinct commitments, which are just commitments where the commitment is much shorter than the message, turn out to be extremely useful. And classically, they're equivalent to C or HFs, collision-resistant hash functions. So the question is, can we construct succinct QSCs? Well, turns out that we can, and it's going to crucially rely on this idea that binding is the same thing as the D register hiding the underlying state. So whenever you're trying to hide a state from someone, the obvious thing to do is to just encrypt it. So take any secret key encryption scheme where the keys are much shorter than the message you're trying to encrypt, and we could just encrypt psi using the shorter keys, and then send away the keys. And this is going to hide the state from ourselves, from the D register, so it's going to be swap binding. So in a little more detail, how do we build a secret key encryption scheme for a quantum state with short keys? Well, one thing you could do is you could just take your short keys, use a PRG to stretch them into long pseudorandom strings, and then one-time pad your state using the large pseudorandomness. Okay, so formally I've written the state here. It's using the superposition over the keys as the commitment and the one-time padded state as the decommitment. Okay, and actually as some extra bonuses, this scheme has some extra features that were not present for the classical succinct commitments. So first of all, it's completely non-interactive, whereas for a CRHF, it inherently requires the receiver to first send a key to the sender. For our succinct commitments, there's no such requirement. And furthermore, we only rely on one-way functions, right? Because we can build a PRG from one-way function, so we don't need to rely on CRHFs, which are believed to be stronger. At this point, we've seen our definition of binding for QSCs, and we've seen how to construct succinct QSCs satisfying our notion of binding. So what can we do with these? Well, one of our main applications is going to be for succinct arguments. Classically, succinct commitments enable succinct arguments. So a succinct argument is just a scheme where a protocol where a prover can convince a verifier of some possibly complex statement using a very small amount of communication. So succinct means that there's a short amount of communication, and the word argument here signals that the protocol is only sound if the prover is computationally bounded, which is in contrast to a more usual proof, which is just always sound. Okay, so how does this protocol work? Well, the main idea is we're going to tree commit to a PCP. So a PCP is just a proof that is checkable at a small number of locations. So, of course, we could just convince the verifier by sending the entire PCP proof, but we want to reduce the communication. We want to be able to send a very small number of bits instead, and have a small number of total amount of communication. Okay, so this is called Killian's protocol, and the basic idea is first the verifier is going to send a key for some succinct commitment or collision-resistant hash function to the prover, and then the prover is going to just group their PCP into little blocks and hash their way up the tree. Okay, like this. So in here, these arrows indicate the top things are commitments to the bottom things. Okay, so at the top, the root is going to be a commitment to the entire PCP, and the prover is going to send this to the verifier. But the key property of this is that now, if the verifier asks for a query at a specific location Q, then the prover can open that location by just opening the commitments on the way up to the tree. So you can imagine if this was a deeper tree, then this would be a huge savings compared to just sending the entire PCP. Okay. Now all the verifier has to do is verify that these things hash consistently up to the root that they were given earlier, and then check that the PCP openings were valid. And this will serve as a PCP check. In this work, we'll show that succinct QSCs plus quantum PCPs imply quantum succinct arguments. So a quantum PCP for us just means a quantum proof that's checkable at a small number of locations. An example is any classical PCP, because a classical proof is in particular a type of quantum proof. And the quantum PCP conjecture states that quantum PCPs exist for all of QMA. Okay, so our protocol is going to be pretty much a direct quantum analog of the classical Killian's protocol that we just saw. So the prover is just going to use succinct QSCs to commit their way up a tree to some quantum root and send this to the verifier. Now the verifier can ask for quantum PCP checks and then receive the openings as before. So this is inspired by a protocol suggested by Chen Mavasak. Okay, and as a bonus, because our succinct QSCs only rely on one-way functions and don't require keys, we're actually going to get a 3-round protocol rather than the classical 4, and it's going to be based on one-way functions, or potentially even weaker. Okay, so the question is, how do we prove our protocol sound? Well, let's start with the classical version. How do we prove the classical Killian's protocol sound? So first of all, the concern is that the prover might be responding to queries adaptively rather than according to some fixed proof. So we know by the soundness of our PCP that if the prover responds according to the actual fixed PCP proof, then the protocol will be sound. But maybe depending on which query you ask the prover, they might change which response they give you. So in order to prove that Killian's protocol is sound, we're going to fix this issue by using the security property of the commitment. So the security property of the commitment is what guarantees that the prover is responding according to some fixed proof that's consistent. Okay, so how do we actually show that the prover is responding according to some fixed consistent proof? Well, we will actually build an extractor which uses black box access to the proof to extract some consistent global proof, and then we're going to show that if you answered queries according to this consistent global proof, you would have the same success probability as the actual prover did. Okay, so this is how we're going to show that our protocols are sound. And the question is, how do we actually build such an extractor? Well, classically and quantumly, the technique is called rewinding. For a classical adversary, rewinding works by just asking the prover different queries, just repeatedly asking the prover new queries and recording whatever responses they give you. And then after each query, just resetting their state back to where they were after they had sent the commitment, but before you asked them the query. For quantum adversaries, the proof turns out to be a lot more subtle, but it was recently done by CMSC. So in the quantum case, the concern is that measuring the prover's response could potentially damage their state, and now you wouldn't have any way to reset their state back to the place it was right after sending the root. But CMSC show that, well, maybe you can't reset their state, but at least you can repair it back to a state that's just as good or almost just as good at answering responses correctly. So here we'll ask for a query, receive the openings, and we'll write down the results. We'll measure the results that they sent us and then store them somewhere. Rewind, and if it's a quantum prover, repair it, and then send a new query and receive a new response, measure it again, and we keep going like this. Now, how does this rewinding idea fare in our quantum setting where we want to have a quantum proof? Well, we're sort of right off the bat run into a problem, which is that we shouldn't be measuring our proof anymore. Like, we shouldn't be measuring our proof, at least not on the standard basis, and really we shouldn't be measuring it in any basis, because the basis in which one wants to measure the registers of a quantum PCP might depend on which query we're asking. Really, we need to be extracting a quantum state, which should serve as a proof. So how do we extract a quantum proof? Well, the basic idea is we're going to use swap-based rewinding, which is new to our paper. And the key idea is that if we, instead of measuring the responses, we're just going to swap out the states onto our own register, then we can undetectably record the whole state using the swap binding property of our succinct commitments. So now, every time we ask for a query, we'll go and write it down on our own internal, we'll go and swap it out with our own internal register where we're going to store the entire PCP. So we ask a query, we swap it out, and then we're going to use CMSC repair again to get the prover back to the successful state, and then do the same thing. Okay, so at the end of this, we should have an entire PCP, or at least most of the quantum PCP, written down as a regular quantum state, and we'll have completed the extraction. But there's an important subtlety with this argument, which is that CMSC repair requires that the extractor has to both have the ability to verify decommitments, which turns out to be necessary in order to do the repair procedure, and at the same time, they shouldn't be able to break binding, because if they can break binding, then the guarantee that swap binding that we can swap out the proof undetectably is sort of going to fall apart. So on the one hand, verifying decommitments would seem to require the C register. On the other hand, an inability to break binding would seem to require not having access to the C register. So these things are clearly in tension with each other. And the main technical step of our paper is going to be resolving this tension. So we do this by proving that swap binding remains hard, that a commitment scheme remains secure, even if the adversary is given an oracle that allows them to both verify commitments and act on the underlying message. So we call this seemingly stronger notion of security oracle swap binding, and show that it generically follows from swap binding. And then, once we have this, it only remains to show that CMSC rewinding can be implemented, CMSC style rewinding can be implemented using such an oracle, and we're able to do this as well. So in summary, we've seen a simple definition of binding, which is that committing to a state psi is erasing psi from the center's point of view. We've seen that our definition makes it easy to build new constructions of QSCs, and it also formalizes the old folklore construction for a hiding and binding QSC. And finally, we've seen that succinct QSCs enable quantum succinct arguments. So thanks for watching, and don't forget to like and subscribe for more content.